Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today, we're starting our new and improved MCAT General Chemistry playlist. This first lecture, we're going to call it Chapter 0, is going to provide some background information and a quick refresher of some important terms and concepts in case it's been a while since you've taken chemistry. This chapter will set us up for success as we cover the next 12 chapters. And here, specifically, I'm going to go over units of measurement, temperature, classification of matter. We're also going to go over subatomic particles. Here we'll discuss protons, neutrons, and electrons. And then finally, we will also cover atomic mass versus atomic weight. And here we'll do a little bit of stoichiometry as well. So with that introduction, let's go ahead and get started with this first objective titled Units of Measurement. Chemistry obviously involves experimentation and measurement. And in order to communicate those measurements, it's important to pay close attention to the units that are used to describe them. Every measurement must be expressed in appropriate units. Now, the agreed upon unit system among scientists is the SI system, which is based on the metric system. And there are 7 base units in the SI system. I have them listed here. Now, all other units that you might be thinking about or are familiar with, those are just derived units which are obtained by combining the SI base units. So let's go over the SI base units. For mass, the SI base unit is the kilogram, abbreviated kg. For length, the SI base unit is the meter, abbreviated lowercase m. For time, the SI base unit is the second, and it's abbreviated lowercase s. The SI base unit for temperature is the Kelvin, and it's abbreviated capital K. For electric current, the SI base unit is the ampere, and it's abbreviated capital A. For amount of substance, the SI base unit is the mole. It's abbreviated MOL. And then last, but certainly not least, we have luminous intensity with its SI base unit being the candela, abbreviated CD. Now, we can use SI units to obtain derived quantities, some good examples being volume, density, and electric charge. Let's focus on volume here. Volume is the amount of space that's occupied by an object. It's equal to the length times width times height. And you would express length in units of meters and width in units of meters and height in units of meters. So what you have here is meters times meters times meters, and here you get the derived units for volume to be cubic meters. Now, units, they're frequently modified through the use of metric prefixes. You can add these prefixes to make it more reasonable to refer to different values of length, mass, or time, depending on the system you're referring to. So looking at this metric prefix figure, we can go over a couple of important ones. Kilo is 10 to the power 3. Milli, this is 10 to the power minus 3. Micro is 10 to the minus 6. Nano is 10 to the minus 9. Now again, we just said that we can add these prefixes to make it more reasonable to refer to different values of length, mass, or time, depending on the system you're referring to. So for example, if you are referring to a human cell, you don't want to say, hey, a human cell is anywhere between 0.000001 and 0.00001 meters, when instead you can say that a human cell is anywhere between 1 to 10 micrometers. All right? And so when we're saying that this value 0.000001 is equal to 1 micrometers, that just means that 1 times 10 to the minus 6 gives us, if we move the decimal over 6 places, 1, 2, 3, 4, 5, 6, it gives us back 0.000001 meters. All right, so this is what we're talking about when we use metric prefixes to make it easier to refer to different values of length, mass, or time. With that, we can move into our second objective on temperature. When we get to our chapter on thermodynamics and thermochemistry, understanding temperature becomes really important. But what exactly is temperature? In everyday language, we often use the term temperature to convey the sensation of hotness or coldness. However, in the realm of thermodynamics, it has a more precise significance. At the molecular level, temperature correlates with the average kinetic energy of the constituent particles of a substance. On a macroscopic scale, the temperature differential between two objects, it directs the flow of heat. Heat will spontaneously move from regions of higher temperature to those of lower temperature. Now, how does this knowledge translate to the practical function of thermometers? Well, thermometers, they've been used to quantify temperature of substances since the 18th century, and some well-known substances include Fahrenheit, Celsius, and Kelvin. Both the Fahrenheit and the Celsius scales are based on the phase changes of water, which makes them super convenient for everyday use. Now, the Celsius scale, it defines the freezing point of water to be 0 degrees Celsius and the boiling point of water to be 100 degrees Celsius. The Fahrenheit scale, instead, it defines the freezing point of water to be 32 degrees Fahrenheit and the boiling point of water to be 212 degrees Fahrenheit. Now, the Kelvin scale, this is most commonly used for scientific measurements, and it is one of the 7 SI base units. It defines, as the zero reference point, absolute zero. This is the theoretical temperature at which there is no thermal energy. And it sets the freezing point of water to be 373 Kelvin. Now, here we have to note something important. How do we convert between these units? So if you want to calculate Celsius, but what you have is Fahrenheit, you can plug it into this equation right here. 5/9 multiplied by Fahrenheit minus 32. Now let's say that you have Celsius and you want to figure out Fahrenheit. We can plug it into this equation right here. 9/5 times Celsius plus 32. Now if you're trying to get Kelvin, after you know Celsius, very easy. Kelvin is just Celsius plus 273. Now, something else I just want to note, when we use a thermometer to measure temperature, it's really essential to recognize that the thermometer, it doesn't just directly gauge temperature. No. It rather gauges the volume of the substance it contains. So common thermometers will often utilize the expansion and contraction of liquids like mercury due to temperature changes to measure temperature. And so that rise or fall of the liquid column of, say, mercury, it will correspond to shifts in temperature. And so you work backwards from there. So just a little fun fact. Now, the next thing we want to talk about is the classification of matter. Matter can be defined as anything that occupies space and has mass. And this is the fundamental material of the universe. Matter can exist in 3 primary states: solid, liquid, and gas. And we can argue plasma, but we don't need to talk about that right now. These states, they're distinguished by the arrangement and the energy of their constituent particles. So solids have tightly packed particles in a fixed structure. Liquids have closely packed particles that can flow and change shape. And then gases, they have a widely spaced particles that move freely. Now, matter is very much complex and organized into several levels. Matter, it can be divided into mixtures and pure substances. Mixtures are physical combinations of 2 or more substances where each retains its individual particles. This can be categorized as heterogeneous mixtures and homogeneous mixtures. Heterogeneous mixtures have visibly different components or phases. So think about a mixture of sand and water, right? You can see the distinct parts. The sand is there, the water is there. You can see it, and it can be physically separated. Homogeneous mixtures, on the other hand, also known as solutions, they have a consistent composition throughout. So think about like salt dissolved in water. In homogeneous mixtures, the individual components, they're not visible. You can't, when you dissolve salt in water, you can't see the salt and the water. You really just see the water. And so they're not visible. And The thing is, we can take homogeneous mixtures, we can separate it into their pure substances, but this requires physical methods like, for example, distillation. Through these separation methods, you can get back your pure substances. Pure substances, they have a uniform and definite composition, and they can be further classified into elements and compounds. Elements are substances that consist of only one type of atom, and they cannot be decomposed into simpler substances by chemical means. So think about like hydrogen, carbon, oxygen, gold. These are elements. Elements are the building blocks of all matter, and they're listed in the periodic table based on their atomic number. Now, compounds are pure substances that are formed from two or more elements chemically bonded in fixed proportions. They have distinct properties that are going to be different from their constituent elements. So, for example, water is a compound and it contains hydrogen and oxygen in a 2-to-1 ratio, H2O. Compounds, they can actually be broken down into simpler substances back into their elements, but using chemical methods. Chemical methods are needed. Now, going back to elements, all right, at the atomic level, matter consists of atoms. This is the smallest units retaining the properties of an element. An atom, it comprises of a nucleus and electrons. The nucleus contains protons and neutrons, and then we have electrons that orbit the nucleus. Protons are positively charged particles, while neutrons are neutral, and electrons are negatively charged particles that occupy the region of space around the nucleus called orbitals. Now, electrons are fundamental particles. Protons and neutrons are not fundamental particles because they can be broken down further. Protons and the neutrons within the nucleus are made out of even smaller particles known as quarks. Now, you don't need to know this for the MCAT. I just want you to visualize this like hierarchy of matter. Quarks are fundamental particles that will combine in specific ways to form protons and neutrons. We're not going to get into the details of that. But this just helps you visualize looking at this. Looking at this, you can begin to understand the hierarchical structure of matter. From mixtures to pure substances, elements and compounds, down to atoms and even their subatomic particles. And that provides us a comprehensive framework for exploring the composition, the properties, and the interactions of all material substances in the universe. And actually, in this next objective, we're going to really be focusing in on understanding atoms and the different components of atoms in terms of protons, neutrons, and electrons. And to motivate this next objective, we want to ask, again, what is an atom made of? And how do the atoms of various elements differ? We know that an atom is the smallest unit of ordinary matter that forms a chemical element. And we know that an atom is composed of a nucleus made out of protons and neutrons, and electrons orbit the nucleus. We already said also that protons are positively charged, neutrons have no charge, and electrons are negatively charged. Now, the protons and neutrons, they define the mass of the atom, while the arrangement and movements of electrons determine the atom's chemical properties and reactivity. Now, the first question we should ask is, well, how did we even reach this conclusion? And it was the overall work of many scientists that actually led us to our understanding of the atom. We start off with John Dalton, who proposed his atomic theory in 1803. He viewed atoms sort of like billiard balls. Atoms of different elements simply differed from each other by mass and nothing else. They could not be subdivided any further. It wasn't until J.J. Thomson's work with cathode ray tubes in 1898 that negatively charged particles called electrons were found to be present in atoms. Then, in 1911, Ernest Rutherford further refined our view of the atom by showing that although atoms consist mostly of empty space, at the center of every atom is an extremely small and dense nucleus, which is positively charged. And he was able to make these conclusions based off of his gold foil experiment. Then Bohr came along and developed his model, which suggests that the negative charges orbit the nucleus of an atom, which is made out of protons and neutrons. There is more to that truly, because we actually can't pinpoint where the electrons are. We can only talk about electron density probability, and this is where the quantum mechanical model comes into place. We can't say that we know where electrons are. We can talk about where is the electron most likely to be found, and this is actually a question that we talk about a lot in chapter 1 of this playlist. Now, with that understanding, a little bit of history, let's really focus on the subatomic particles in a little bit more detail. Again, an atom is the smallest identifiable unit of an element. It is a neutral particle made out of negatively charged electrons moving around a positively charged nucleus. We talked about protons, electrons, and neutrons. Let's focus on protons really quickly. It's found in the nucleus. Each proton has an amount of charge equal to the fundamental unit of charge, which is, by the way, 1.6 times 10 to the minus 19 coulombs. And we denote this as a positive +1 charge that's associated for protons. Protons have a mass of approximately 1 atomic mass unit, approximately. All right, and in kilograms, that is written right here, 1.672 times 10 to the minus 27 kilograms. Now for neutrons. Neutrons are neutral. They have no charge, so their charge is 0. A neutron's mass is only slightly larger than that of the proton, and together, actually, the proton and neutrons of the nucleus make up essentially almost the entire mass of an atom. So here's the mass for a neutron written in AMUs, and this is the mass of neutrons in kilograms. Now we want to talk about electrons. Electrons are really interesting. They move through the space surrounding the nucleus, and they're associated with varying levels of energy. Each electron has a charge equal in magnitude to that of a proton, but with an opposite sign. So we give it a -1 charge. In coulombs, that charge is written right here. Now, the mass of an electron is approximately 1/2000 that of a proton. They are very small, and because of this, because this subatomic particle's mass is so small, the electrostatic force of attraction between unlike charges, so between that proton and electron, is far greater than that of gravitational forces of attraction based on respective masses. Now, something to know about electrons, again, is that they move around the nucleus at varying distances away from the nucleus. The electrons that are closer to the nucleus are at lower energy levels, and those that are further away are in higher shells that have higher energy. We're going to revisit this in the next chapter. Now that we understand the atom, though, all right, let's talk about a couple of important terms that are related to the atom. Atomic structure is defined by 3 critical numerical descriptors. We have atomic number, mass number, and atomic weight. Now, looking at the element on the periodic table, for example, looking at any element on the periodic table, the atomic number, also denoted as Z, is the count of protons in the nucleus of an atom. And this number is fundamental because it determines the chemical identity of the atom. Each element on the periodic table is characterized by a unique atomic number. So if we take oxygen, for example, all oxygens are defined to have 8 protons in their nucleus. That is the defining characteristic of the oxygen element. Now, the mass number, sometimes denoted as A, is the total number of protons and neutrons in an atom's nucleus. neutrons and protons. This sum gives us the mass number. Now, the difference between the mass number and the atomic number is the number of neutrons in the nucleus. And it's important to note that the mass number is not the same as the atomic weight. Now, we're going to talk about atomic weight, but really quickly, I want to show you how else you might see this information communicated. So you might also see where an element is written down, an elemental symbol. So for oxygen, that would be O. And here in the top left corner, you're going to have the mass number, which is about 16 for oxygen. And in the bottom left corner, you have the atomic number written, so 8. Now, let's talk about atomic weight. This is a more nuanced concept. It is the weighted average of all the masses of naturally occurring isotopes of an element. Since isotopes of an element have varying number of neutrons, they also have different mass numbers, but the same atomic number. Atomic weight, it also takes into account the relative abundance of each isotope in nature. So let me give you a proper definition of isotope. Isotopes are variants of elements that are going to have the same number of protons, but different number of neutrons leading to different mass numbers. So if we're talking about oxygen, again, all oxygen atoms, they have 8 protons in the nucleus, but the number of neutrons that can change, and that gives rise to isotopes. Understanding atomic structure and isotopes is really crucial for grasping the bigger picture of chemical behavior. The variations in atomic number and mass numbers among isotopes really influences the physical and chemical properties of the element, which in turn affects reactions, bonding, etc. Now let's go back to atomic weight. Let's spend some time here. All right. So now that we've defined isotopes, let's go back to our definition of atomic weight. We defined atomic weight as the weighted average of the masses of all naturally occurring isotopes of an element measured in atomic mass units. So what we want to do here is break this down because the calculation is not so simple sometimes, all right? So to calculate atomic weight, scientists are going to consider both the mass and the natural abundance of each isotope of the element. So here's how it works. First, isotope masses. First, the exact mass of each isotope of the element is determined. These masses are close to whole numbers, but are slightly different due to binding energy within the nucleus. That's besides the point. We get the exact mass of each isotope of an element. Then 2, natural abundance. Each isotope's natural abundance is then determined. This is the percentage of each isotope that's going to occur naturally on Earth. And then we can do the weighted average. The atomic weight is just calculated by multiplying the mass of each isotope by its natural abundance and then adding these values together. What the result is the weighted average that represents the average mass of all the isotopes as they occur naturally. Let's do an example. So for example, if you have an element that has 2 different isotopes, we're going to call isotope A and isotope B. And you know that isotope A has a mass of 10 AMU and a natural abundance of 90%. And you know that isotope B has a mass of 11 AMU and a natural abundance of 10%. What is the atomic weight? All right, the atomic weight would be calculated as follows. We're going to focus on isotope A. We know that its mass is 10 AMU, and it has a natural abundance of 90%. We're going to multiply that by 90%, but in decimal form, so 0.9. All right, we're going to add that to our isotope B. Isotope B has a mass of 11 AMU and a natural abundance of 10% or 0.1 in decimal form. All right, we're going to add these 2 values together, and what we get is the atomic weight. If you plug this into a calculator, this first one is 9 plus 1.1, and that gives us 10.1 AMU. So the atomic weight for this element that has 2 isotopes is 10.1 AMU. All right, so now we've talked about atomic number, mass number, and atomic weight. There are a couple of more concepts that we want to discuss now that is going to be super crucial before we move on. And that is the following. We want to really properly define atomic mass unit, moles, and molar mass. So we've said AMU and atomic mass unit quite a few times thus far in our lecture. What does that mean? The atomic mass unit is a standard unit of mass that quantifies the mass of atoms or molecules, and it's defined as 1/12 of the mass of a carbon-12 atom. All right, carbon-12 isotope is stable, and its abundance makes it a standard for measuring atomic masses. One atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. The atomic mass of an element, it's usually found on the periodic table, and it's expressed in AMU, and it represents the average mass of all the isotopes of that element, taking into account their relative abundances. All right, so here we're tying in concepts now. Then what is a mole? This is going to be so important for chemistry, all right? A mole is a unit that measures the amount of a substance. So just like the measure 1 dozen signals 12 insert object, whether it's a dozen books, which is 12 books, or a dozen eggs, which is 12 eggs. All right, 1 mole is a unit that measures the amount of substance, and 1 mole of any substance, all right, 1 mole of any substance equals 6.022 times 10 to the 23 entities, and that could be atoms, molecules, ions, etc. This is known as Avogadro's number, and the mole allows chemists to count particles by weighing them. The mass of 1 mole of a substance is equal to its molecular or atomic mass in grams. And that leads us into talking about mass, molar mass. Molar mass is the mass of 1 mole of a substance, element, or compound, and it's expressed in grams per mole. Now that we have defined these 3 terms, how do we connect them all together? And by that I mean, how do we convert from one form into another? So let's start by saying that you know the number of particles and you want to convert that to moles. How do you do that? In order to do that, you divide by Avogadro's number. So you divide by Avogadro's number. If you know the number of moles and you want to go back to number of particles, in order to do that, you're going to multiply by Avogadro's number. Okay, now let's say you know the number of moles and you are interested in converting to mass. How do you go from moles to mass? In order to do that, you're going to multiply by molar mass. Now, if you know the mass and you want to go back to moles, you're going to have to divide by molar mass. Okay, one more layer here. What if you know the mass and you want to convert to number of particles? In order to do that, you're going to have to follow the arrows. First, you divide by molar mass, and then you multiply by Avogadro's number. That's how you go from mass to number of particles. It involves 2 steps. Okay, that's great. What about the other way around? What if you know the number of particles, you're interested in the mass? In order to do that, again, we follow the arrows. First, we divide by Avogadro's number, then we multiply by molar mass. So that is the workflow in order to be able to move from one unit into another. Let's go ahead and tackle an example problem together. This one says, suppose you have 3.011 times 10 to the 23 particles or atoms of argon. What is the mass of this sample? All right, so what we're given is we're given the number of particles, and our goal is to get mass. Let's go back to our figure and figure out what are the 2 steps that we need. We have number of particles, we have mass. All right, we're trying to go from number of particles to mass. This involves 2 steps. First, we divide by Avogadro's number, then we multiply by molar mass. We're going to write that down. First, we divide by Avogadro's number, then we multiply by molar mass. And what we're actually going to set up here is what we're going to call stoichiometry in order to convert all the way from particles to mass in a setup that allows us to cancel and look at how we cancel units appropriately. So the first thing that we're going to write is what we're given. We know we have 3.011 times 10 to the 23 particles. Now, in order to convert from particles to mass, there's an intermediate step where we go from particles to moles by dividing by Avogadro's number. And in order to do that, well, we know Avogadro's number is 6.022 times 10 to the 23 particles per 1 mole. Right? That's our relationship. And what you notice here in this setup is that particles are going to cancel out. We're left with units of mole, but we're not done because the problem is not asking for moles, it's asking for mass. So then we do our last step, which is multiply by molar mass. 1 mole of argon is equal to, what is the molar mass of argon? 39.95 grams. So 1 mole of argon is equal to 39.95 grams. And notice that moles cancel out here. Our remaining unit is grams of argon. This is exactly what we want because it's asking us for the mass of this argon sample. Now what we do to solve this problem is this is just doing the numerator divided by the denominator. So you will, if you're wanting to plug this into a calculator, you will first add in parentheses the numerators, multiply them together. So you're going to multiply this number by this number, close parentheses, then divide by the denominator, which is this number right here, Avogadro's number. And if you plug that into the calculator correctly, what you're going to get is that the mass of this argon sample is 19.975 grams. And there we have it. We solved this problem. Let's go ahead and do another example here. This problem is actually going to motivate our discussion on ions. So let's read it. It says, determine the number of protons, neutrons, and electrons in a nickel 58 atom and in a nickel 60 atom. So let's go ahead and discuss ions first, and then we're going to come right back to this problem. Something to remember is that in ordinary reactions, the nucleus does not change, but the number of electrons that an atom possesses can change. And so it's safe to say that the movement of electrons constitute reactions. And this is going to be a focus of most of our discussions in general chemistry and also in organic chemistry. It's then important to pay close attention to whether a particle is a charged ion or a neutral atom, because an ion possesses properties that are quite different from those of a neutral molecule. An ion is a charged particle resulting from the fact that the number of protons is not equal to the number of electrons. And there are 2 types. We have cations and anions. A positively charged atom is called a cation. This happens when an atom loses an electron. Then we have anions. These are negatively charged atoms. This happens when an atom gains an electron. And it's important to pay attention to whether a particle or a molecule is charged or not, because an ion possesses properties that are quite different from those of a neutral atom. With that being said, let's move back to our problem here that says determine the number of protons, neutrons, and electrons in a nickel 58 atom and a nickel 60. So for our nickel 58 atom, well, let's remember that nickel, the atomic number for nickel is 28. And remember that the atomic number tells us the number of protons. All right, it tells us the number of protons. Now, in a neutral atom of nickel, which is what nickel 58 is here, there's going to be 28 protons and 28 electrons. So the number of protons is going to equal the number of electrons. That means something really important. If we have 28 protons, but 58 here tells us the mass number, we can figure out the number of neutrons by subtracting 58 from 28, and that gives us 30. This is our number of neutrons. All right, so for nickel 58, this is a neutral atom of nickel. 58 is the mass number. The atomic number for nickel is 28. Atomic number tells us the number of protons. In a neutral nickel atom, the number of protons equals the number of electrons. So we have 28 electrons and 28 protons. 58, which is what we're given here, this is the mass number. This is protons plus neutrons. If we know the number of protons, we can figure out the number of neutrons by taking 58, the mass number, subtracting it from the number of protons, 28, and the number we get is the number of neutrons. So that's how we worked through this problem for nickel 58. Now let's do nickel 60, and it tells us here that this is a +2 cation. What that means is our number of protons stays the same because we're still dealing with nickel, and nickel is defined by having the same number of protons, the same atomic number, which is 28. It tells us this is a +2 cation. That tells us how many electrons are lost. Remember, cations form from loss of electrons when you lose an electron, and this is a +2 cation, which actually means you lose 2 electrons. And so the number of electrons is no longer 28, it is going to be 26. That is the number of electrons. All right, fantastic. And now we have the mass number here, which is 60. We can figure out the number of neutrons by taking 60, subtracting it from the number of protons we determined, and that gives us the number of neutrons. 60 minus 28 is 32. So this has 32 neutrons. And there we have it. We've solved this problem. And with that, we've completed all of the topics that we wanted to in chapter 0 with our background information that we need so that we can be successful in future chapters. I hope this was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.